All right, if your organization relies on local AI models, you're going to want to pay close attention to this. Welcome to the Explainer. Today, we're diving into a critical vulnerability dubbed Bleeding Llama. It affects Ollama, and it has massive implications for your enterprise data. We're looking at a near maximum severity flaw, a CVSS 9.1, officially tracked as CVE-2026-7482. Discovered by the team at Sierra Research, this is a big one. So we're going to unpack exactly how this memory leak works, analyze the real-world business risks, and lay out the immediate defensive actions your SecOps teams need to take right now.
Let's just jump right into the blast radius. 300,000. That's the estimated number of exposed Ollama servers sitting out there on the internet right this second. And here's the kicker. By default, Ollama listens on all interfaces with absolutely no authentication required. None. That means we've got 300,000 potential entry points for threat actors to exploit this without needing a single credential. So yeah, this isn't some theoretical, maybe someday risk. It's a massive, highly accessible attack surface today.
Okay, really quick, here's our roadmap for this explainer. 1. The Bleeding Llama threat. 2. Enterprise data risk exposure. 3. Mechanics of memory leakage. 4. GGUF manipulation and exfiltration. And finally, 5. SecOps detection and defense. Let's get into it.
Section 1. The Bleeding Llama threat. So the core issue we're dealing with here is that a remote, completely unauthenticated attacker can easily extract the entire heap memory of an Llama process. And honestly, they can pull this off using just 3 simple API calls. Now, if you're not familiar, heap memory is basically the active scratchpad where an application stores data while it's running. Llama has become the go-to enterprise standard for running open source models like Llama and Mistral locally. And usually you do that precisely to keep your sensitive data on premises, right? Well, this vulnerability completely flips that local security advantage on its head, turning what should be a secure local deployment into a wide-open spigot.
Moving on to Section 2, Enterprise Data Risk Exposure.
Let's be clear, the compliance nightmare here is very, very real. We aren't just talking about attackers scraping abstract, meaningless machine code. An attacker can scrape highly sensitive user messages and prompts. Just imagine for a second an employee pasting proprietary source code or confidential customer contracts into your local AI. Well, that data is just sitting right there in memory. The leak exposes system prompts housing your core business logic, host machine variables that might contain API keys, and even outputs from connected tools like Claude Code. Basically, an attacker can learn almost everything about your organization just by secretly observing your AI inference process.
Section 3. Mechanics of memory leakage. Let's look under the hood to see how this actually happens.
So normally, the Go programming language is heavily fortified. If a program tries to read memory outside of its designated boundaries, Go will immediately panic and crash just to prevent a breach. It's a great safety net. However, Go provides a specific package that's literally called unsafe. It's an escape hatch designed for high-performance memory operations. And when you know it, the one place Ollama uses this unsafe package is exactly where this vulnerability lives. By prioritizing mathematical optimization during model creation, Ollama temporarily throws standard memory safety right out the window. This allows a malicious process to blindly read past the intended buffer and straight into that highly sensitive heap memory we just talked about.
All right, Section 4, GGUFF manipulation and exfiltration. Let's see how attackers actually smuggle this payload.
To really understand this attack, we have to look at the package it arrives in, which is the GGUF file. GGUF is just a standard file format used to store large language models efficiently. You can think of it as the brain of the model. Inside are tensors, which are essentially multidimensional arrays of numbers. But here's the catch. Because GGUF is just a binary format, there's no inherent validation. An attacker can manually crack a malicious GGUF file and tweak its header to falsely claim it holds millions of elements, even when the actual data inside is tiny.
So, here is the end-to-end execution of the attack in 3 steps. Step 1. The attacker uploads that maliciously crafted GGUF file to the Ollama server using the /API create endpoint. Step 2 is the trigger. Because the attacker artificially inflated the tensor shape in the file, when Ollama tries to process and convert the data format, the loop blindly reads past the end of the buffer. And boom, it scoops up all that sensitive heap memory. Finally, step 3 is the getaway. The attacker uses the /API push endpoint to push the newly created, memory-stuffed model right back out to their own external attacker-controlled server.
Now, you might be thinking, wait, wouldn't processing the data scramble it because most format conversions in AI are what we call lossy, meaning data gets corrupted along the way? But the attackers use a really clever trick. They set the malicious file's tensor type to F16, which is a 2-byte format, and then they request Ollama to convert it to F32, a 4-byte format. Moving from a smaller byte size to a larger one is a perfectly lossless conversion. By forcing the specific F16 to F32 mathematical jump, the attacker ensures that the stolen enterprise data scooped from the heap isn't corrupted at all during extraction. The data lands on their server exactly as it was sitting in your system's memory.
Which brings us to Section 5, SecOps, Detection, and Defense.
Because this attack relies on those specific API endpoints, your monitoring strategy needs to be absolutely razor-sharp. First up, you need to catch the infiltration phase. Do this by actively monitoring the API/create endpoint for abnormal model creation. Specifically, look out for models being built from unexpected files rather than standard registry pulls. Second, you have to catch the exfiltration phase by monitoring the API/push endpoint. Remember, Llama is typically a local tool, so pushing models out is highly uncommon in secure enterprise environments. You want to flag any API/push requests that are directed at external, unverified URIs. Honestly, if a local model is suddenly trying to push data to a random web address, you likely have an active breach on your hands.
And this brings us to the ultimate question for your security leadership. Are your local AI models secretly bleeding enterprise data? The bleeding Llama vulnerability is proof that just deploying locally does not automatically guarantee privacy. So I highly urge you to review your Llama deployments today. Lock down those API endpoints behind proper authentication and get strict monitoring implemented immediately. Stay secure out there and make sure your AI infrastructure is actually yours. Thanks for joining us for this explainer.